Hello, hello. Do we have 4 viewers? Great. Let me know what you hear in the chat. No. I'm streaming physics, dude. Hello, welcome. This is there for people watching. I just see me. Arlene, hello. Hello. Yeah, I got a new app for my laptop so that way I can try to make the live streams a little more attractive. And it is lagging like crazy. But yeah, I got a new app too. That way these streams can be a little more attractive for you guys. And that way you're not staring at me trying to project a thing on another thing and then it looks really blurry. So hopefully this looks a little better. But yeah, I got a new app too. That way these streams can be a little more attractive for you guys. And that way you're not staring at me trying to project a thing on another thing and then it looks really blurry. So hopefully this looks a little better. Yeah, I learned things in on the internet. Okay, but yeah, so let's get started on this session. Like I mentioned earlier, this is gonna be mainly just you guys asking me questions and me trying my best to answer them to best prepare you for this final. I posted up all the quizzes that you guys have taken, so chapters 8, 9, 10, and 12, or yeah, the work for 12. Um, so if you guys have any questions on those, I am willing to answer those. So if you guys have any questions on those, I am willing to answer those. Yeah, I posted them under homework in the modules area. It says that they're visible to you guys. Test, test. 1, 2, 1, 2. We still here? Yeah, it says. Oh, hold up. Test, test. 1, 2, 1, 2. We still here? I never published the entire thing. Yeah, it says. Oh, hold up. I never published the entire thing. But yeah, those were also in files, I think, even if I didn't publicize that. But yeah, those were also in files, I think, even if I didn't publicize that. Because all the files say that they're published, but just the section in module says that it's not. It should be available now. Say that they're published, but just the section in module says that it's not. It should be available now. Yay, it's there. Yay, it's there. Delicious drinking sounds. This is ASMR with Yaya. Delicious drinking sounds. This is ASMR with Yaya. Oh, you can hear it. That's really awkward. I'm sorry. Maybe I can make it not as loud. Oh, you can hear it. That's really awkward. I'm sorry. Okay, that was just testing the feedback. Okay, so you guys see it? Do you like want some time to work on it for a little bit, or do you guys have questions that you want me to start answering? That was just testing the feedback. Okay, so you guys see it? Do you like want some time to work on it for a little bit, or do you guys have questions that you want me to start answering? The backside of 12 is just concept stuff. Honestly, for that one, I can just read off what I have for my answer key. The backside of 12 is just concept stuff. Honestly, for that one, I can just read off what I have for my answer key. Issues with chapter 12 because the calculations we had to add the mass of the melted ice. Yeah, I mentioned that a lot during supplemental though. That's mainly because when you're considering the phase change between ice and water. Yeah, so here, let me draw it. That's mainly because when you're considering the phase change between ice and water. So here, let me draw it. In a brush, yo. So this whole shebang, where down here you have ice. Right here you have phase change. So this whole shebang, where down here you have ice. Here you have water. You have another phase change. And here you have gas. So remember here at this point right here, I'm just gonna so remember at that point, you're going at 100 degrees Celsius. And then down here at this bottom part right here. This feels like Khan Academy, it's really weird. At this bottom part right here, you're at 0 degrees Celsius, meaning that you're going through different processes. These two sections are going to have different equations. And this right here is where you use Q is equal to MLV. And this one right here is Q is equal to MLF. Ah. Right? But right here at these slopes, that's when you use your MCAT equations. So that one's going to be Q equals MCAT. Because there's a change in temperature. As long as it's able to rise and become something else, you can use your MCAT. But if it stays stationary, like for example for water, where it stays like at 100 degrees Celsius while it's changing from water to gas, or while it's changing from ice to water, you have to use these other equations. So, the reason why you had to add the 2 up was because this ice is already here at this phase change point. It's somewhere along here. And it's already turning into water. So you have to consider adding the ice with the water. So I gave you guys 8 grams of ice, which was a mistake. It was supposed to be 2 grams of ice and 8 grams of water, but whatever. So ice, water. You were supposed to consider 10 grams of water for your Q equals LF, Q equals MLF equation. Or MILF, if that helps you remember it better. Hey, it's a weird equation, but it helps you remember it, right? Hey, it's a weird equation, but it helps you remember it, right? Yeah. That's what DePerl did in her calculations, if you look at it. Yeah. We trade places. I made DePerl take my quiz, so that way she could tell me if it was a bad quiz or not. Yeah. That's what DePerl did in her calculations, if you look at it. Yeah. We trade places. I made DePerl take my quiz, so that way she could tell me if it was a bad quiz or not. Oh no, she ended up using it for MCAT. That's weird. You're supposed to be using it for MLF, not for MCAT, because for MCAT, that's specifically just going for water. Hence why you have a specific heat for water. So, Why would you use it for MCAT? Because you're going through a phase change and that ice is turning into water. Add water and ice for the phase change. Because the ice is changing into water, it's kind of becoming water. So the specific heat for ice is a little different than for water. I kind of gave it to you guys in the chart during the quiz. Yeah. Ice at 0 degrees Celsius has a specific heat capacity of 2.010 joules over grams times degrees Celsius. Hence why you can't use purely ice with the same heat capacity for water. Yeah. Ice at 0 degrees Celsius has a specific heat capacity of 2.010 joules over grams times degrees Celsius. Hence why you can't use purely ice with the same heat capacity for water. So that's why I'm kind of confused on her calculations there. But that's what she's been doing in class, right? So that's why I'm kind of confused on her calculations there. You use it for MCAT because since the ice is already melted, it's all water at that point, right? But that's what she's been doing in class, right? Exchange of 2 grams would be MCAT. Yeah, 2 grams of water is for sure MCAT, and you're using the specific heat of 4.184. Why is water added to phase change? And melted. Yeah, 2 grams of water is for sure MCAT, and you're using the specific heat of 4. Wait, what? I'm sorry, Eileen. I'm kind of confused by your thing. I thought just 8 grams ice would be doing the phase change, and the 2 grams water would be doing MCAT. Yeah, that's what's supposed to be happening. And then 10 grams ice plus water would be MCAT. Not necessarily. Yeah, that's what's supposed to be happening. And then 10 grams ice plus water would be MCAT. Not necessarily. Sure. For sure. We have the gold, which I gave to you guys in kilograms. You had to convert it to grams because the specific heat was in grams. Unless you wanted to convert the specific heat to kilograms, which I personally thought was a pain in the butt. So it becomes 5,000 grams. And you multiply that by the specific heat of gold, which was 0.129. For sure. We have joules gold, which I gave over, what was it? Grams times degrees Celsius. We're going to work in Celsius for this one because that's what I stole from UCI. And then change that to the change in temperature, so TF, because that's what we're trying to find, minus 386. I can hear myself talking, it's throwing me off. And then change that to the change in temperature, so TF. Oh, she kept it in Kelvin. Oh my gosh. She is going to give me. In degrees Celsius, you should have gotten a final answer of about 113 degrees Celsius, which is the same as 386 Kelvin, so. Oh, she kept it in Kelvin. Oh my gosh. I like to keep my units consistent, though, because I am a butt. In degrees Celsius, you should have gotten a final answer of about 113 degrees Celsius, which is the same as 386 Kelvin. Right, so this whole shebang right here, I like to keep my units consistent, though, is all gold. So that's pretty straightforward and simple, right? So this whole shebang right here is all gold. So that's pretty straightforward and simple, right? It's so funny, I can't see who's here. The part that we're struggling with is here, where she has in her work 10 times 4.184. The part that we're struggling with is here, times TF. She has in her work 10 minus 273. 0.15 again. That she's doing this in Kelvin. Oh my gosh, I told her it was in Celsius. Why does she keep working in Kelvin? Why 0.15? But yeah, it's 0 degrees Celsius because that's where it started anyway. And then she has 8 times 10 to the power 3, so she converted the 8 grams into kilograms. Wow, none of this is consistent. I'm slightly annoyed. This is supposed to be 8 grams. Oh well. 8 times 10. No. I don't know what. Okay, yeah. So that's kg. And you times that by the specific, or not the specific heat, the LF that I gave you guys, which was 334. I think it was kj over kg, right? Oh, look, it's my hello here. Ah, shipping. How would you convert the specific heat? Was the whole point to work in Celsius? I gave you guys Celsius because that's what was given in the UCI thing. If you wanted to convert to Kelvin, you pretty much just do it the same way you would convert Celsius. So just add 273. Yeah, because this is the grams of ice, so this is the mass of ice. That looks nasty. I should invest in a tablet. So this was mass of ice. And then over here is supposed to be ice plus water, I guess. Which is silly, because in my quiz, she marked me wrong for having it different. Or for having it similar. Because I'm pretty sure my quiz from when I took it has circled around. You guys have seen it. Oh, yeah, I'm writing off screen. Give me 1 second. I can fix that. Okay, that's why we were confused when we started your quiz. Yeah, like, you see the correction that she made for me. On my quiz, she told me that this was wrong. She told me that I had to use this guy, so the 10. Whereas, and that I was supposed to just use water on this one. So that would have been the 2 grams. Times 10 to the power of 3. Oh. People are getting way too drunk out there. They're slamming the wall. Okay. But yeah, so that's where I guess where I went wrong. And since Deprell's writing the quiz this time, make sure you follow her stuff. So when it comes to the MCAT equation and you have some kind of phase change, quiz, I say. It's actually a final. Because a final is totally a quiz. It's basically 4 quizzes put together, right? Anyway, so since DePrell's writing it, let's understand what's going on here. So here, I guess what she's trying to do is that she sees that ice is already transforming into water. Like I think it was Ashley who said it. Um, the ice is turning into water, so you just consider that entire mass, and then you combine it with the specific heat of water, and then do the whole shebang for MCAT. Whereas when it comes to the phase change, just purely use the mass given to you of the ice. No, yeah, okay. So she just graded me wrong, I guess. Oh, this just out. Yaya was put as supplemental instructor because of flukes. That's why I don't know anything. I cry. No, but yeah. LF would be used for ice of water. Everything is a lie. Yeah, LF would be used for ice because that's ice that's changing into water. Everything is a lie. Yeah, LF would be used for ice because that's ice that's changing into water. I'm gonna show us I wrote mass. Yes, this is a mass. This is supposed to be purely ice. Uh-huh. Yeah, you might have to recalculate it then. But yeah, so basically that was the whole process of part B when it came to the water and the ice and the piece of gold. You would just basically have to use Q of gold plus the Q of ice with the water, and then Q of just ice as it's melting. I think she kind of writes it on the answer thing too, that you have a Q of water and the Q of the melted ice, which is basically just water, so you combine it to get your final answer. Does that make sense? Pretty much any problem in your book that has to do with phase change is one way for you to practice. I don't have your book, so pretty much all I have are just my quiz questions and the question that I made. I have last year's quiz questions. I don't know if that'll help. That's air density. That's chapter 13. Yeah, last year they didn't have the same kind of problem. They had a bunch to do with PV equals nRT, which is ideal gas law. So I really don't have any other questions for chapter 12. Unless you guys have one and you want to send it to me and I'll work on it. So I really don't have any other questions for chapter 12. Unless you guys have one and you want to send it to me and I'll work on it. For chapter 10, which is energy, I remember her specifically telling me make sure that they understand the change in energy or the conservation of energy. For chapter 10, which is energy, okay, I can do chapter 10 quiz when the three balls are colliding together. If I can find it. In my great big book of everything with everything inside. Wait, what problem with three balls colliding together? That was chapter 9. Fired. So you want me to go over momentum? So you want me to go over momentum? It's like a 5-second lag right there. Okay, let's do the ball problem. Dude, you have your tablet?
A drawing tablet?
Yeah.
I was gonna use it.
Oh, never mind.
That's fine, go for it.
No, it's okay. I got my mouth.
Stop! You're using it for educational purposes.
Porpoises?
Draw a stupid game.
What if you are a stupid game? I don't even know if it'll work on mine.
I don't think we can try it.
Alright, well, I guess I'll try it then.
We'll try it to see what happens.
Please hold while we,
No, that part connects computer, this part goes in tablet.
Okay. Oh man. Do I have another USB port? I think it goes over here. I need a computer with more USB ports. Because this one is breaking. Eh.
That's not gonna break on me.
Huh?
Hold on.
Please hold while I transfer you. There we go.
The pen broke.
You broke it!
I just clicked it! There it goes.
Please hold while I transfer you.
Okay, let's see if it works. The pen broke.
You broke it!
I just clicked it! There it goes. Okay, let's see if it works.
Okay, we're back. That'll do it.
I'm currently coming up with custom work.
Had trouble with chapter 10 quiz. Okay, so let's do it. We had this ball, which was going. Had trouble with chapter 10 quiz. Okay, so let's do it. We had. For a second. This ball, which was going. I need to keep an eye on the chat, so I'm just gonna put this on the side. Okay, so we have this ball. This is gonna be ball number 1. I don't like this. I can't control the colors. Oh, we're number 1. Oh, and then it makes it tiny on this thing. 1 second. Ugh, this is annoying.
Or at least more people that we can draw.
Alright, good enough. That's ball number 1. Then we got ball number 3. Need my brush again. It's going that way at 3 meters per second. And this one was 30 grams. And then we had this one was 40 grams. This is going to be ball number 3. This is going to be ball number 2. Are you guys still there? I know I kind of lost signal for a minute. Are you guys still there? I know I kind of lost signal for a minute. Okay, cool. Yeah, you can hear me. Alright. So in the after portion, we know that there's going to be just this big old ball. I'm just going to make it. We're here, we're here, we're here. And it's going to go in some direction. We don't know what direction. We're just going to take a wild guess. I'm going to guess this way. Why? Just 'cause.
Crap, how do you spell
And
that?
it's gonna go a certain angle from the horizontal. So now we have to start figuring out what's on X and what's on Y for this. Oh, before I continue, what kind of what kind of collision is this? What kind of conservation of energy? Oh, before I continue, what kind of what kind of collision is this? What kind of conservation of energy? Yeah, inelastic. I'm just trying to make this bigger. Okay, cool. Editor. I should be able to move this to the side. There we go. Beautiful. Beautiful. Alright. So it's an inelastic collision, meaning that we're going to be using this equation. The M1V1 plus M2V2 plus M3V3 is all equal to this final thing, which is M4V4. This M4 we know is going to be equal to all the masses, so M1 plus M2 plus M3 is equal to M4. With me so far? Yeah, cool beans. Oh, I love this. Okay. um, so we have this inelastic collision. We already have all that jazz figured out. The only other thing that we have to figure out is who's on X and who is on Y. Right? We only have this first ball right here that exists on both X and Y. So this is going to go all the way back to chapter, I think it was chapter 3, where we start working in 2 dimensions. So I'm going to do this in purple so that we can keep track of which ball we're solving for. I am sorry for my horrible skills. This is 45 degrees, and this is 4 meters per second. Fun little tidbit, if she does give you a problem like this and you have a 45-degree triangle, realize that these two sides are the exact same measurement. So if you solve for one, you get the other. So remember, to solve for y, you have to remember sine. Shoot. Remember sine. Remember sine. Remember sine. Opposite over hypotenuse. This is y. Right? So for y, what do you end up getting? You get like 2.83.
Hopefully this works. Should we go to the other chat? Should we move to the other chat?
That's meters per second. That's how much they're traveling in the y direction. If you really, really, really wanted to, thanks Ashley. If you really, really, really wanted to, you could go through the whole shebang again and try to solve for x, which is gonna be up here, which would be adjacent over hypotenuse. But watch, if you plug it into the calculator, it's going to be the exact same thing. I'm just giving you this tidbit so that way you can save some time when you're on the final. So once you solve for one, you basically solve for both of them. So, let's separate it on x and on y now. On x, we have ball 1, which we figured out what the velocity is on x. So the mass, we have to convert it to kilograms, always. So to kilograms, you just bounce it 1, 2, 3. 0.04 kg. Let me zoom in on that. Ugh. You know when you have like a burp that's stuck in your throat and it just won't come out? That's exactly what's happening because I really don't want to burp into the mic and I know it's really nasty, but TMI.
Alright, we all ready?
Meters per second.
Come on in, bro. The water's fine.
So all this is the first one. The second ball is not moving on X, so we're just going to ignore the second ball. And then we have the third ball, which is moving on X, but in the opposite direction. So the mass, I think, was 30, so now it's 0.03 kilograms. And it is going 3 meters per second. And then we considered this final part, so that M4, which I said was the mass of M1, M2, and M3 all put together, which I think is 0.09. And then VF. Thank you, Ashley. Or not VF, but V4. Right, so then you pretty much have all your variables set in. Now you just gotta find V4 on X. Then V4 on X is equal to... I ended up getting 0.258. Anyone else get that? Yeah, because the direction of the ball is going in the opposite direction of what we really need it to. So to the left in this case, whereas this one is traveling towards the right, we have to cancel them out.
Okay, you ready to go? Alright, starting in... Oh wait, no, both of you are still not here, huh?
Right, 2.83.
I put it in Lords of Roleplay. It's literally the first link I put in.
And I'm neglecting third ball because third ball is moving purely on X, but I am going to include the second ball because it is moving on Y. So 0.02. Now, could you guys tell me what is wrong with the setup I just made?
It'll be fine, don't worry about it. Just keep playing it. There you go. You fossil? Oh my god. It's fine. Alright, I'm starting it up. In 3, 2, 1. Okay, we have the chat. We have the chat over here to guess.
Yeah, you need to neglect for ball 1 because it's going in the opposite direction. It's going south, as opposed to north like ball 2. And you still gotta include for V4, which is 0.09.
You have to guess.
And we're trying to find VF of Y.
Keep talking your pins, Moldy. PTA.
I think for this one, I ended up getting negative 0.813 meters per second, which is V4 on Y.
Yes,
Did you guys get the same thing?
Were you not listening? Oh, yeah, there we go. Hell yeah.
Oh, did I not put 2? Oh, sorry. Yeah, it's going 2 meters per second. Thank you for that. Okay, so we have Vx and we have Vy. Now you just gotta figure out which direction it's going. Vx is positive, so we know it's gonna be going towards the right. And we know that since Vy is negative, it's going to be going south or downwards. And then this is back in chapter 1 when you had to do your vector additions. Meaning you're going to have a resulting vector right here. And now you just got to solve for it. This was 0.258 meters per second. And this side is the same as this side, so this is 0.813 meters per second. I can neglect the negative because I already considered the direction. And you can use Pythagorean theorem. You can use inverse tangent to find your theta, and then use another trig function to find your side. But this is that whole situation where you decide, okay, which strategies am I going to use? I ended up using Pythagorean theorem, which gave me a V4. Meters per second. And then I ended up using tangent to solve for theta, which gave me a theta of 72.5. And that should basically have solved the problem for chapter 9. Does this help make a little more sense? Yeah, that's funny. On my streaming thing, on the program that I'm using, it says I have 0 viewers, but then on YouTube it says I have 7 people watching. Yay! Okay, so that's basically momentum, the conservation of momentum. So remember, for chapter 9, there was impulse. So impulse was the same as average momentum. Um, you also had momentum being in the form of, well, the conservation of momentum being in the form of inelastic collision and elastic collisions. What else was in chapter 9? I'm trying to remember. Let me go through my notes. Hold on. People need to stop drinking because they're like crazy singing outside my dorm and it's really cringy. Yeah, so there was impulse, which was the force times a change in time, and then impulse was also equal to a change in momentum. Yeah, then you're talking about total momentum within a system, inelastic and elastic momentum, conservation of momentum, and then the law of conservation of momentum, which is basically no change in total momentum of the system. Total P of a system is conserved. So no matter what, as long as there's a collision involved, with that collision, all the energy is going to be within that system.
You guys better freaking get this, I swear to God.
Another thing that you should probably look at is how momentum and energy are both related, specifically kinetic energy. Because both kinetic energy and momentum have this conservation uh, conservation property to them. And I think it actually applies to all energy, not just kinetic energy. Yeah, because it's I think the first law of thermodynamics where conservation of energy energy cannot be created or destroyed. It's going to stay within the system. And then second law refers to entropy, which is basically if you do lose energy, it's not because it disappeared, it just went into chaos. It went into our atmosphere, basically. And we didn't teach you guys how to calculate for entropy, so I wouldn't worry about it. Remember that work is mechanical energy. It's basically a transfer of energy from a system via push or pull. It's also considered a transfer of energy between a system and an environment via temperature when it comes. Oh, I'm sorry, that's heat. Sorry, I can't read my own handwriting. Heat is non-mechanical, whereas work is mechanical. So heat is non-mechanical because it refers to the molecules or the energy within the system between the actual object and the temperature around it. Work is mechanical, meaning you have to actually push or pull on an object in order to get some kind of energy going.
Number
And then one thing
10.
that a lot of you guys really didn't catch on, I don't know if it wasn't really highlighted in your PowerPoint, but temperature is basically an average of the energy within a system. You're not really getting that exact not getting that exact measurement of energy, otherwise your thermometer would never be constant. So it's just getting like an average reading of the energy within a system, or in this case heat.
Wait till we have a freaking quiz.
Yeah, conservation of energy also refers to like when you convert, yeah, PE into KE or KE into thermal energy, so all that jazz. Um, so conservation of energy, whether it's related just purely to energy or also to momentum, I would highly look at that because she wanted to make sure that you guys understood that information before the final.
So
Excuse me. Is there anything else you guys want me to cover? I don't even remember what I said. Repeat what part? Chapter 10? For Ashley, basically I was talking about the conservation of energy. So, it was mentioned earlier with momentum, how momentum can be conserved, whether elastic or inelastic, right? So, when it comes, if momentum's involved, since kinetic energy is an energy related to speed, you're probably going to relate momentum with kinetic energy. Um, so if she ever asks you a question about the conservation of energy within a collision, those are the two factors you need to consider, as well as impulse. When it comes to conservation of energy in general, you need to be able to identify which energies are being active when whatever situation's going on. So like in chapter 10, when you guys did that problem with the spring, that was like potential energy of spring turned into kinetic energy turned to thermal energy, etc., etc. And you would have to be able to use that property of conservation of energy to be able to solve for it. Ke to thermal. Let me see if I can find the paper I was looking at when I started spouting that nonsense. Thermal expansion, Ke to normal, Ke to thermal. I am not normal. Well, that last part I was looking at was basically where work is mechanical energy, so energy that requires movement. So it's either push or pull. That's the whole work thing. Heat is an energy, but that's a non-mechanical energy. That's just referring to the molecules that are working. And there's that transfer of energy involved within the system and the environment. Oh, okay, I already answered it. Cool. Now I can get back to the other question, which was what was it? Chapter 10, quiz number 2. As shown in the figure, a bullet of mass of moving horizontally suddenly strikes a block of wood. Mass of blah blah suspended. What am I finding? The length of the spring. What is type of collision is this? Well, you guys can answer that one. What type of collision is it?
There we go.
Inelastic, right. Ash is over here. Inelastic! I got this! I love it. I love that image. I don't know if that's how you're actually reacting, but I'd like to believe that. We know that this length is 2 meters. So therefore this length right here, this guy right here, I'll probably highlight it in yellow. Hey, give me that. It's the coffee. The coffee's getting to you. I got you. So this guy is also 2 meters because it is the same string. Um, I'm sorry, I still have the image of Ashley just like with a cup of coffee. Elastic. Oh my gosh, I need to draw that. I need to make that a thing. Okay. Um. Anyway. They told us that the bullet lodges in the wood and together they swing upward at a vertical distance of 4 meters. So this distance right here compared to the bottom, 0.4 meters. Well, sorry, this is no longer 1.5 actually.
That's so. That's so bad.
Because there's a bullet over here somewhere. And that bullet has a mass of 0.01 kg. Right? So then this actually became something else. So it became 1.51, right? That new mass, it's just M1, which was 0.01 kg. And then M2, which was 1.5 kg, is going to be M3, 1.51 kg. I'm not breathing into the mic, am I? That's like, I'm like really paranoid about that. I'm really sorry if I am. Please tell me. If I am, I'll change mics right now. Okay, cool, thanks. So, um, we know that this hypotenuse right here is our 2 meters, and we're going to have a shape. Oh, shoot. Okay, dude. Need you to. They can hear you. Thanks. It's all good. No. Okay. I'm sorry, dude. It's just for like another. It's until 8:30ish. Okay. It's the ghost. You're a ghost, dude. Okay, so we have our hypotenuse here, and we know that it lifted just a little bit by 0.4. So we know that this new hypotenuse or leg here, the ghost from yesterday. Oh my gosh, that was scary. Don't even mention that. um, so we have 2 meters, and then we're gonna subtract that by that new height off there. And we're gonna end up getting a new height. So this leg right here of 1.6 meters, right? So now we have two sides to this triangle. And what are they asking? What is speed of the bullet just before it? Oh shoot, we didn't even need to do that. I am so sorry. I'm horrible. Well, now I feel a little better if she were to ask you this kind of problem and she asked you to solve for the angle. Now you know how to approach this. So yeah, if she gave you this kind of problem, she asked you for an angle to solve for it, then just use whatever trig function is required to find the theta. In this case, it'd be cosine, and you can use that. I don't know, momentum, something. She'll use her imagination. She'll figure it out. Anyway, so it says, what was the speed of the bullet just before it struck the wooden block? So because we know this is inelastic, we have to consider m1v1 plus m2v2, etc., etc. Right, m1v1, that would probably be the bullet, so let's make it bullet. Bullet! I'm gonna get rid of this. You guys know that that's 4.4 meters. 0, 1. Now we are trying to solve for this v1 right here. We don't know it. m2 is going to be the block, so 1.5 kg. Times v2. Which was 0 because it was stationary. It would just hang in there. And then m3, which I mentioned earlier, is 1.51. And then v3, was it given to us? Bullet lodges, the length of the string is this. Oh, we don't know v3 either. This is quite the pickle. Whatever shall we do? So basically we have an equation where it looks like this. Vi or v1. Then 1.51 kg v3. So when it comes to momentum, this is the equation that we have. So remember that thing I was mentioning about earlier when I was just rambling about energies and conservation of them? What can we do since we have this momentum equation with two unknown variables? Ah. Hello? Hello? Anybody there? Jesus, I lost 2 viewers. What a shame. Well, since it's taken a while, we know that momentum is conserved, but also energy can be conserved. And since both of these have to do with movement, so if there's movement, what kind of energy should I use? KE, yeah, using the conservation of energy. So basically, it's going to be KE of the first guy plus KE of the second guy is equal to KE of the third system. KE plus PE? Uh, I can see why you would use PE because this area right here gives you a height. Oh. Let me double check. I think I took a picture of her work. When did we take the chapter 10 quiz? I forget. That's chapter 9, so I'm guessing this one was chapter 10. No, I didn't take a picture. That's a damn shame. That's a good question. Should we use PE to solve? Because it did go up a bit. Oh. I think you actually do consider it. Yeah, you do. So that's my mistake right there. Make sure that you write down on your, when you do the stuff, that it's KE plus PE. Because you do have a height. It is converted from kinetic energy just purely here, and it is lifted at the end. Thank you, Ashley. She took off points because in. Ah, damn. Well, yeah, this is the conservation of energy that you need to be considering. So let's plug it all in. 1/2 m for system 1, which we said is bullet, so 0.01 kg, times v, which we said was what? Oh, that's what we're trying to solve, haha. And then we had the second equation. Oh my goodness. Ah! One of my online friends was watching, and now he's like bugging me. That's rude. He's a rude dude. Beat him up. Okay. This one didn't have velocity, so it's 0 and we can neglect it. And then the last one, 5.1 kg. Oh yeah, 1/2. I forgot the front. And then V3 we don't know. Then we add that to potential energy, which is M, which is still the same M. 1.51 times mg squared, mgh. So 9.8. And then h was 0.4, right? Yes, 0.4 meters. Okay, so here all you have to do is simplify it. So what I would do is first I would simplify this and then multiply both sides by 2, which will just increase this by 2 and then get rid of my halves. So let me know what you get. I'm going to do it here on the side. I got that would be joules plus 1/2 1.51 V3 and then 1/2. I mean, I guess you could divide this whole thing by 2, but I don't know if it would get you the same thing. I'm just trying to play it safe. Anyway, so multiply this entire thing by 2. That should cancel out this guy with this guy. And then this guy gets distributed in. So this guy with this guy, and then this guy gets doubled. So this times 2. Let me know if my algebra is wrong. V squared. Oh, thank you, thank you, thank you. Squared, squared, squared. Good thing I haven't had to square anything yet. Then you get 1.51. And then this became 11. I love the little cool emoji because you're just like, you're welcome. And then like puts on the cool kid glasses like, yeah! I live on the internet for too long. I need a life. I love the little cool emoji because you're just like, you're welcome. And then like puts on the cool kid glasses like, yeah! I live on the internet for too long. I need a life. What's 35.037? Anyway, so I think what would help here is because this equation at the top, I did it wrong. Delete that. It never happened. Oh, I can actually delete it. There you go. Anyway, using this equation up here, you can either substitute the VI or the V3 in here to help solve for whatever you need. Ashley swore it said dumbass, and it's all like, oh, are you sure you want to show this on your stream? Anyway, so I did V3. I think I did? Yes, I did. Because I want to solve for VI anyway, or for V1. So I did 0.01 V1 over 0.51 is equal to V3. So then I plug that into this equation here. So let me make some room. Excuse me. Oh, the Yoshinoya is coming back. Oh yeah, I tried Yoshinoya for the first time. It was disgusting. Yoshinoya, please do not sponsor me. Actually, gross. I guess someone else doesn't like Yoshinoya. Oh yeah? It's good. What do you mean? Oh no! Never say another foul word about Yoshinoya again. I'm going to dislike, unsubscribe, report you to YouTube. I'm going to dislike, unsubscribe, report you to YouTube. See, I got so distracted by being reported that, like, I wrote it wrong. How could you? I'm being harassed by my viewers. Stop all this bullying. To Prolix Yoshinoya, she finds out that I don't like it, and she's like, "Oof, you're fired." And I'm just like, "No." Oh yeah, I forgot I need to square this. To Prolix Yoshinoya, she finds out that I don't like it, and she's like, "Oof, you're fired." And I'm just like, "No." No one likes Yoshinoya. Oof. Ask her. Oh my gosh. Blocked and reported. Oh shit. Well, there goes my YouTube career. Yes, I can use all the profanity I want. I'm going to just display boobies on here. Just kidding, I won't. Okay, so actual math here. You gotta square this whole fraction. Job requirements includes proficiency in physics. Thanks for Yoshinoya. And speaking a little bit of French, I guess. Because I remember when I first met her, that's how I tried to start talking to her. I was like, "Oh, I heard you speak French. I've been trying to practice my French, so can I talk to you?" And she's like, "This girl's weird," and she never talked to me again. And then physics happened. Ten to the power of -4. And this would be this would be v1 squared, and then 1.51 squared. DePro likes to eat dark chocolate. I know that for a fact. Other foods, she likes to eat salad without dressing. And if you eat dressing, she will judge you very harshly. I know because I came into class eating salad and I put a little bit of dressing on it and she was all like, "No, you already ruined the salad." Other foods, she likes to eat salad without dressing. And if you eat dressing, she will judge you very harshly. I know because I came into class eating salad and I put a little bit of dressing on it and she was all like, "No, you already ruined the salad." The 0.01 is coming from the momentum equation we did up here. Here, I'll box it for you. I'll box it for you. I'm gonna box it for you. The 0.01 is coming from the momentum equation we did up here. Here, I'll box it. So then I put it here. Oh shoot, I'm still writing in box. No, don't save! Technical difficulties. Okay. Oh shoot, I'm still writing in box. No, don't save! Technical difficulties. Okay, so then I end up with this. I should have squared it correctly. I think it is. Now what you can do is try to use this to simplify this. So can I... This basically just becomes 1.51 again anyway, I think. So this becomes 1.51 again. So let me go over here to the side. And that becomes 1 times 1 times 10 to the power of negative 4 with v1 squared all over 1.51. Then you add your potential energy, which you guys know it's over here. I'm just not going to write it yet. Now what do you want to do? The 1 times 10 to the power of negative 4 is me squaring 0.01. Yeah, thanks, Arlene. You got it. Even though your taste in Asian food is not the best. No, just kidding. Any ideas on what to do next? I wonder if snails are good. They're very chewy, at least from what I've heard. Why are we talking about food? You're gonna make me hungry in the middle of a stream, and then you're gonna hear me crunching on stuff, and that's just awkward. I think what I would do. We're still working on the problem. I'm sorry. I believe the final answer for this one. Oh, I exited out of it. We're still working on the problem. I'm sorry. I believe the final answer for this one. I'm looking. The back of the problem, right? Ah, no, what happened? Someone got it. I forget who. Oh, of course it's her. So the final answer should be 422.5 meters per second. So the final answer should be 422.5 meters per second. Yeah, so she used momentum. What the heck? One quarter. That's mass, so 1/2. What the heck was your logic here? I am so confuzzled. Okay, I'm not gonna look at that because that's confusing me. I'm just stuck on my algebra right now. What was the final answer again? Apparently, the final answer is 422.5 meters per second. Because we're looking for the initial velocity of the bullet. I wonder if I did this. It would be minus. Because I got a potential energy that's different than this person, but they got full points, so. Is equal to my fraction. Then what I'm going to do is just multiply all this. I'm going to multiply all that by 1.5 just because I really, really want to get rid of that fraction because it's getting annoying. And then just 1. Then V1 squared. Alright. So then I would distribute all that. So then, times that by 0.01. End up getting 0.0151. V1 squared minus 11.8384 times 1.51, 17.87, or 0.88 if you want to round up. And that's all equal to 1 times 10 to the power of negative 4 V1 squared. Does that look about right? Did I do my algebra wrong? Because now what I want to do is get these two together. Yeah, both of the VI's should be squared. So combine like terms. That should be 1 times 10 to the power of negative 4 v squared. They're both the same. So that's that. And I'm going to subtract 0.0151. That should give me a negative number. Good, it did. And then from here, just divide. So negative 17.88, divide that by negative 0.015. I got 1,192. I'm not exactly sure how this person ended up getting that other number. 422. Oh wait, because it's squared. Ha 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 ha. I still have to square root it. I got 1,192. I'm not exactly sure how this person ended up getting that other number. Oh wait, because it's squared. Ha 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 ha. I still have to square it. Answer. Nope. Then I get something really super duper small. That is strange. Hmm. Because for V1, I ended up getting 34. Yeah, I got 34.5. I'm trying to see where I went wrong. Do you want me to explain to you guys how she did it? Or the person who got it correct? How they got it? Okay. So I'm just going to erase all this. So this person took the conservation of momentum, so the whole shebang of like M1, V1. This is bullet. Ah. This is bull. Let. And then over here, M2, V2. And this was block. So I'm just going to put BL for block. And then M3, V3. So that whole thing is still there. And then she plugged in her values, which was 0.01, like how we had it earlier. Times V1, because that's what we're trying to solve. Plus 1.5. And then there was no velocity initially, so we neglected. That's 0. And then M3 was still 1.51. And then V3 because we don't know it. So they had the same equation we did when it came to what we were substituting in. So 0.01 V1 is equal to 1.51, which is V3. So I guess they just simplified it by going 1.51, divide that by 0.01, and that ended up being like V1 is equal to 151. V1, V3. Oh, so it is safe to do that. So this was their equation for momentum. So this is mo momentum. Then they did a whole conservation of energy portion where they have PE plus KEI. So this was their equation for momentum, which is all equal to PE final plus KE final and they also included thermal energy. Which is why I'm kind of like, what the heck are you doing? This one for sure you can neglect because there was no height in the beginning. Because HI is 0, so you can neglect that. And I guess she's looking at the kinetic energy of the block, because then it just becomes, then she just writes 0, or sorry, I'll write that over here, plus 1/2 m times 0. Because I guess the block, since it's not moving. Yeah, that's all they have written for that. But then underneath it, they have E thermal, which is MGF, MGHF, minus MVF squared. And then she plugged everything in. So 1.51. Shooters. Times 9.8. Times height, which was 0.4. Minus 1/2 times mass, which is 1.51, times VF squared. So 1.51 times 9.8 times 0.4. Yeah, so basically what they did was, this was the PE final. And that turned out to be 5.91 joules minus, and then the kinetic energy, which is just 1/2 times 1.51 times VF squared. I'm guessing she just neglected ETH, because that's all she has written down right there. Then what she does is that she changes this to be 5.91 joules is equal to 1/2 1.51 times VF squared. And then it's just solved for VF. By the looks of it, they ended up getting a VF of 2.79. And then when they found VF, they plugged it back in to this equation right here. And plugged in VF for V3. So the part that for me doesn't make sense is that you're basically starting off here with like a bunch of variables, right? You're given a value, but then over here, you're basically starting off with 0. So my question is, did she pretty much just assume all this was 0 and try to find a VF that would give me an eventual energy of 0? Anyway, so you would plug it all in, or not that equation, sorry. It was this equation right here, the momentum equation. So then you would get V1 is equal to 151 times 2.79 meters per second. So then that V1 should give you that 400 whatever thing it was. That 422. 0.5 meters per second. And DePerl really liked this one. She even gave it 2 extra points. No, she gave the 2 extra points for the concept part. So if I understand she wants us to get this whole conservation of energy thing. If any of you guys can figure it out and let the rest of us know what's going on. Because up to here, it all makes sense for me, the momentum portion. But then here, I don't understand why she's considering thermal. And I don't understand how she's able to get that PE equal to that KE in the end. Yeah, I found someone who did it the way I did, and she ended up getting it the same answer as me. Which is why I'm just like, what's going on? Honestly, though, if you do it the way that we did it earlier, she'll still give you points for understanding that there is a conversion of energy, especially if you have your momentum part set up like this, and especially if you have this energy portion set up, and you write down all the conservations of energies. So when it comes to the final, I kid you not, she gave me like a little example of how she normally grades quizzes. I'll read it to you. So the first part of my problem for the bonus quiz when it comes to the calculations, she wants you guys to write formulas. If you write down formulas, that's a point right there. For the second half, so with the pendant, put in ice water and all that for my quiz, she gave you 2 points if you drew the curve, 2 points for writing down the conservation of energy, so realizing that whole 0 is equal to all the Q's that were involved, so Q gold, etc., etc. Then another 2 points for setting up the equation, 2 points for solving, and 2 points if you got the correct answer. So if you pretty much write down everything, all the reasoning that you have behind a problem, you'll get majority of the points anyway. When it comes to this, so for here, we wrote down this equation here, so that's 2 points. This one over here, that's the same 2 points. If we drew what was going on, so, but in this case she gave us a picture, that wouldn't really help. Just drawing a before and after picture. B, A, that's another 2 points, so that's 4. Setting up the equation, so this right here, putting down the equation, setting it up and all that, and then plugging it in. The actual solving would probably be this part right here, and then getting the right answer is the only part where you would struggle with. So if you understand this method, I would go for it. If you're gonna go with the other method that we've been working with, just make sure that you explain your reasoning as you go through it, so that way the more you get on paper, the more points she can give you. So if you understand this method, I would go for it. If you're gonna go with the other method that we've been working with, just make sure that you explain your reasoning as you go through it, so that way the more you get on paper, the more points you can give you. I'm trying to see if anybody else got the same answer. Are there any other questions other than this one?
I forgot my keys.
GG, bro.
Sorry.
It's all good. Okay. Yeah, I'm going through this. No one else got that velocity. Strange. Like, literally only one person got that answer. I don't know. I got 2 people got the same answer as me. 3 people. I don't know. Any other tips, particular questions we should focus on? Tips, questions. So, make sure you review mechanical versus non-mechanical energy, what properties follow with that, so the whole heat and temperature thing again. For chapter 8, I would look specifically to resilient forces, so spring force and frictions. Don't worry about torque, that's not on there because we have not covered it. So yeah, for chapter 8, mainly just know your fun equation, so Fk equals mu n. Your spring equation, FSP is equal to negative K delta X. So Hooke's law. What is a restoring force? You don't have to worry about Young's module, she didn't go over that. For chapter 9, again, it's the whole what is impulse, what is momentum, what is conservation of momentum, how does that all relate, especially to energy. Go back to chapter 12, I ended up getting 106. Can I go back to chapter 12? I'd have to draw it all out again because I don't save these pictures. I'll save this one and post it. Let me erase this though. Actually. Okay, so I'm gonna post this one so you guys can look at it later. And then make a new one. I'll send you a pic. My phone should be charging. I haven't got your text, Giselle. Real quick before I go back to chapter 12, let me just finish the overview. So chapter 10 is energy and work. Review what exactly work is, the mechanical energies, non-mechanical energies. What is kinetic energy, potential energy, transformation of energies, thermal energy, potential energy of a spring versus potential energy due to gravity. What is heat and what is temperature? There's thermal energy again. Energy in collision, so that's going back, relating all energies related to momentum. Power, that's going to be on there, so make sure you know how to calculate for power rates. Phase changes, when it comes to those problems, make sure that you draw out the phase change chart because she will give you 2 points for that. Ideal gas law might be on there, probably not, but you never know. Basic stuff from chemistry, that's all related to thermodynamics. Make sure you understand how to convert the density of water. I don't think you really have to worry about pressure and how to calculate for it. You remember your MCAT equation, so your heat equations when you're going through just calculating for heat and calculating for phase change. I don't think you really have to go through volume expansion and linear expansion. If she does put that on there, volume expansion is just referring to an object that is expanding in all 3 dimensions. So like, for example, blowing up a balloon. Whereas linear expansion is just like, think of the bridge. Remember the interlocking picture, or the little grates that you see on the bridges? That's linear expansion, where it just expands in 1 dimension. And then most definitely go over calorimetry, which is basically what we did on chapter 12. That's all the stuff with the water, and metal is transferring energy to the water. You got your heat transfers, your 3 mechanisms, which are conduction, convection, radiation, and then there's evaporation, but we don't really go into that. that's pretty much it. Because we don't go into chapter 13 at all, so don't worry about it. But yeah, that's pretty much the overlaying stuff, at least the big ideas that I remember her going over when it came to chapters 8, 9, and 10. So yeah, I'm just gonna go back to chapter 12 and see what's going on there. If you guys want to stick around to see that, you're more than welcome to. If not, you are free to leave. I really hope this has helped you out as much as possible. I wish you luck with all your studies, not just your physics final, but all other finals. Um, I know you guys have your biochem and your, oh yeah, mainly biochem and ochem that are coming up, right? So there's that. Remember to get lots of sleep, because if you're tired, you won't do well at all. Okay, Giselle, I got your picture, so let's work on that. Do 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 do. What did you do? Got 5,000 grams from the gold. Okay, you got that. You got your TF. You do 113 degrees. Alright, so let me,